see you guys that haven't done this for 2 years in front of a live audience. My name is Balázs Kégl, and I will talk about model-based reinforcement learning today and tomorrow. It's good that you guys are separated. It's actually, maybe we can dance because there is so much floor here. So if any time you need to stand up, feel free. It's 4.5 hours is long, even if it's chunked into 90 minutes. And I also want it to be interactive, so let's use this occasion that we are in the same room and discuss. Honestly, I don't think I have 4.5 hour material in my slide deck, so it will only work if you have questions, and maybe you can even challenge some of the things that I will say. This is a joint work with my colleague Albert, and Gabriel is a research engineer, and Othman is an intern who is going to do a PhD with us. And it's all done in the Huawei research lab in France, Paris. So first, introduction. So you can see some links there. If you want, you can go there and check out what I'm blogging about, for example. So I've been doing machine learning since '95. Most of it in academic research labs. So I was teaching in Montreal, and then I moved to France in 2006 in a physics lab, actually. So I was doing machine learning in an experimental physics lab working with physicists. If you know some of my work, we did a huge Kaggle challenge in 2014 on Higgs boson. And the most interesting part is that in the last 5 years, so I joined Huawei in 2019, 2 years ago. In the last 5 years at CNRS, I was the head of the Center for Data Science, where our mission was to connect machine learning and AI to sciences and put technologies into sciences, build pipelines. And I started to see that a lot of times the problems are not technical, but organizational and managerial. So we started to work on processes, how to put AI into domains where AI is not present yet. Of course, in the scientific context, it was like climate science or medical sciences or economy. I'm sort of doing the same thing at Huawei now. So I'm on the network side of Huawei research. This means that I'm not working on the phone applications. I'm working on applications related to telecom. So Huawei's original business is telecom, building like 4G, 5G, 3G mobile applications. So this is you will see that I will talk about it a little bit, the applications. And it turned out that these organizational issues are the same in industry as in sciences. And so why it's important for this talk, because I want to connect the technical part to the human part of how to do technology that you can then give to humans to use. Because if you don't do this, then it will not work at the end. So very interestingly, what happened there is that I faced this problem of too many choices. Like, if you are in machine learning, you can maybe decide whether to work on reinforcement learning or supervised learning. But when you go out and try to apply AI to sciences, you have to choose between economy, climate science, or medical science. And it turned out that this was like an important thing for my development, because I realized that to decide what you work on and why is much more important than actually solving problems. So I will talk about this a little bit too, and how it relates to the topic the technical topic that I will do. So right now we are about 15. It's fluctuating because we have interns and PhD students. 6 or 7 research scientists, research engineers, and 3 PhD students. And it's a mix. It's an applied research team where we publish on high-level conferences, and we also work on business problems. It's a nice mix. And I just put this in because we are constantly hiring. So this is like the team composition. We are hiring permanent researchers after your PhD, postdoc level too, research engineers before PhD, and PhD students. interns. If you're doing your PhD, we are also having internships from the fall to the spring, like two slots for every year, where you can do an internship with us during your PhD. So the lab is growing quite fast. It's nice to see this, and it's also it's not an IT company, so it's very interesting research in the sense of we are not. It's an industrial company, and in an industrial company, although Huawei is close to IT, there's a lot of engineering, but it's still we are making stuff, and so putting AI into non-IT, it's a challenge. So the class will be so 3 parts, not equally 3, but around 3 questions. And if you know Simon Sinek, I'm following a little bit his line of reasoning of why, what, and how. So I will talk quite a bit about the why, because this is what I feel is important, that how you decide what research you work on is important. And most of the time, when you come up in your careers, at least in my case, it was a lot of times ad hoc. I had some ideas, I published it. I had some other ideas, I published it. It was not very clear what would be, if somebody asked me why, I would just say because I had this idea and it was interesting. And so when you work in an industrial or even in a scientific setting where there is some goal beyond AI, this question becomes important. And I feel now that I'm leading a quite large team, is that it's important to also have, for the team to know where we are going and why. So the topic of the course is reinforcement learning and model-based reinforcement learning, but I want to explain you the exact setting, how we came to this. Okay, I like to start my talks with this citation from a guy called Gianni Vattimo. It's a philosopher who is talking about Heidegger in the quotation, but it's not by Heidegger. So the concept of interpretation is all here. There is no experience of truth that is not interpretive. I do not know anything that doesn't interest me. And if it does interest me, it is evident that I do not look at it in a non-interested way. So what does it mean? It means, so a lot of times when people go into sciences, there is this notion of like chasing the objective truth, trying to get to the truth. And what this citation says is that, yes, once you figured out what the question was, the scientific method gives you really good tools, not necessarily to get to the truth, but at least get rid of or decrease the self-deception that you can get, or the biases that we have. But the whole thing starts with why. Why are you working on a problem? And there are two connections to what I'm going to talk about. This one is just, as a human, as a researcher, how do you decide what you work on? And the second one is, if you want to do AI, how will AI decide what is interested for it? Right now we are giving the interest to AI, even if we go into reinforcement learning where we have like a goal to achieve, let alone supervised learning where it's completely like even the data is given to the function to learn, so the AI doesn't have any notion of willing or wanting to do something. In reinforcement learning, it's one step further, where you can design a goal, but it's still coming from outside. So, so why I'm in model-based reinforcement learning today? It's partly because my dream is to move from what I would call propositional AI, functional learning. I give X and Y, and I want somebody to learn it, to procedural, a goal-oriented AI, where I can just give a goal to the agent, and the agent figures out particularly what data set it needs for learning it. So that's a huge step. In my view, it's still very far from what we do as natural AI, but it's a huge step for AI. I mean natural intelligence, not natural AI, of course. So this is one of my motivations why I'm in reinforcement learning today. The second one is that my day job is working on engineering systems. I will talk about this a lot, what I mean by an engineering system. And we want to automate them. So it's like self-driving engineering systems. I would even put a higher goal, which is like self-aware engineering systems that know about their own inner state, have sort of emotion-like things like fear when something is going wrong and they have to do something. So those kind of notions that we can borrow from human intelligence and cognitive sciences. And the last point is, it's also very interesting. How many of you actually have seen pipelines that were implemented in industry or in sciences, machine learning pipelines? One? So most of you are students, right? So if you go out in a company, let's say I take the example of Criteo because I know them pretty well. So Criteo is a French company who is sort of doing the same thing as Google, but it's a more specific case. They are optimizing ads. Okay? They're optimizing ads means they decide if you go on a web page, so user and website, and there's a slot for an ad, what ad to put there. And their primary goal is to put there an ad where your click will be the most probable. Right? So they want to know, more or less, for every ad that they have in their contracts, what is the probability that you will click? Given that you are you, so they know a lot about you, and you are on that page, so they know a lot about that web page. So it's a function learning problem. You have features of the web page, features of the users, features of the ads, and you have to classify it. You give a probability of click-through. Now, they learn it, of course. The big thing is that Criteo started to do machine learning like 10 years ago. So they have to train a function with all the historical data, right? Now, what happens is that this is like a very clean machine learning problem. If you are in a benchmark, you publish, it's, you know, X and Y are given, you learn it, you improve it, etc. But for Criteo, the problem is that the world is changing. And that function, your probability of clicking through on an ad, changes because you change, the world changes, you are on another web page, you are in another state of mind. So it's even worse when they learn the function and they start putting ad into the system. They are such a big player that they change the system, so there's a feedback loop. So the probability of click-through changes because of their actions. So even if they are in sort of like supervised learning, it starts to feel or smell like reinforcement learning because they have a goal and the world is changing. And this is a very common thing in industry. You are not just learning a function, put it up and then it runs, but you have to retrain every X hours, X days, X years. It depends how fast the world moves. Okay, so the thing of a static data set and function learning that we learn on in the textbooks of machine learning is not true in reality. It's very important what data set we use, how often we retrain, what we do with the previous model. So all these kind of things which come from the evolving world. So the questions that like model-based reinforcement learning is, or the setup that I will talk about, the particular setup which is called iterative batch, is something that's also close to how supervised learning is done in the industry. So see, these are the three motivations I have. I have to say that this given, it's like a post hoc narrative that I have. When I arrived into Huawei, I had like 10 different things that I was interested in. And the way I filtered was I was looking at, you know, what the BUs want and what the BUs will want in 5 years, because we are still a fundamental research team, so we have to think a little bit ahead. Okay, so the way I ended up in RL was in this. And so I will talk about this a little bit on the next slide on the meta, but just to summarize. So this is like even like a higher level view. It's not only for this course, but in general. So the big questions, if you go out and apply AI, is how the AI generates value. What problems should we solve? knowing that most of AI research is on known problems with known benchmarks and you're just improving. So this is like a completely other ballpark when you have to think about how to allocate your time and where do you want to be in 5 years. It needs another mindset than what we usually have in research. And finally, that again, I will talk about this in the particular context of the presentation, is that if you really want your algorithm to work, then you have to think about the organizational and management constraints. So I have a blog on this actually. It's probably my best cited thing ever, more than any of my papers, is that I describe this like in a 5-minute read, how to do this, more or less. Okay, so the first is that you derive the problems from the imagined workflow that you want to use it in. Once you have the workflow, there are some people who are saying actually that first implement the workflow A to Z, put the AI blocks, put something very simple there, and then start with that. And then when it's done, then you start iterating on the solution for that particular block, which can be like a classifier. And this is a non-technical expertise. So if you go to any team that has to do this, it has to implement AI in real life, you need organizational experts. Okay, so my last slide before starting actually the course is this one, some meta about the presentation itself. So I'm not an RL expert, okay? When they asked me to give a summer course here, I was thinking about what to talk about. I could have talked about something that I know better than reinforcement learning, but I decided this because this is what excites me today, and this is actually forcing me to formulate the story that I'm working in, so it helps my thinking. One of the things that you will not get here is breadth. So I will not cover model-based reinforcement learning in a very broad way because I don't know it in a very broad way. Okay? In general, so that's one of the things when you go out to machine learning today, there are just too many papers. So what I decided to do instead is going deep and telling you the story. So from this story, okay, no, there won't be any theory either because I'm not that much interested in theory. Originally, I'm coming from like a machine learning theory school, like in the 90s, and I gradually went towards algorithms and then went towards applications because that's where I feel I have the most impact. So what I decided to do is to show you this 2-year process we went through, including how we came up with the problem we wanted to solve. Because this will give you not only some insight into what model-based reinforcement learning is, but also into what the process is. And still, since most of you are starting your career, that could be interesting to see how we thought, what were the steps for identifying the problems, defining it, narrowing it down, because if the scope is too big, you go nowhere. Narrowing it down, and then designing the tools to answer the questions we had. Okay, but what questions we had is also important. So the paradigms, there are, let's say, 3 big paradigms in AI or in general in science. One is the theoretical, where you have some notions of experiments and you want to make theories about it that make predictions. A lot of math, right? Then there is the experimental methodology, which of course is coupled to the theory because theory gives you the hypothesis, or at least some of the hypothesis comes from theory, some others come from intuitions. So you have this experimental scientific methodology where you have a scientific question and you decide it experimentally. You want to see whether it works or not mathematically, but you design an experiment that answers your question. So a lot of sciences do this, including physics, biology, etc. And the AI, in my view, today is mostly, partly, that much more than theoretical, it's an experimental science. So questions are answered experimentally. But there's a third paradigm which is interesting, which is what I call engineering paradigm. In an engineering paradigm, you don't really answer scientific questions. You want to optimize, you want to solve a problem, you want to go straight to the best solution for that problem, given that the quality is well defined, the metrics, so you know what is the best, right? So I will move between these two, the engineering and the experimental scientific paradigm. They both work by looping experiments, but their goal is a little bit different, right? When you want to solve the problem, you go ahead, you have branches, you discard them because they are not good, and you go ahead to the solution, whereas in the experimental scientific paradigm, you might want to know what happens in those branches, like why this is better than this, right? And so we are constantly moving this. I will explain you why in a later slide. Moving between these two. So what we went through is to identify the problems to solve, and by problem I mean a big problem, like 5 years from now, maybe. Look around for solutions because they might have been solved. If not, design solutions on your own, and then design well-controlled experiments to understand elements of the solutions. It's sometimes called ablation in machine learning. Okay, the last one is that, and we can actually start now, is I'm hanging out a lot on YouTube, and okay, there are some excellent people who give really good talks, but what I really like is the discussion format. So I know it's sort of we don't know each other, and you don't know me, and you might be afraid to ask questions. It would be nice to break the ice. So what I thought about, maybe it's completely out of what you used to, is to turn to each other in pairs and have 2-3 minutes just to introduce yourself and tell to each other why you're here, okay? It's not, you don't have to publish it, you don't have to say it to anybody, just between two of you. And this is just to make this a little bit less one-sided, you know? I think it will break the ice, and then we can also get into discussion, okay? So I give you 2 minutes, and we start then. Okay, thank you, everyone. It went great. I've never done this in my life. I actually learned it from my partner, who's a singer and who is doing workshops. And if you are hanging out till Friday, she will give a workshop, a creativity workshop, an interactive creativity workshop for those who are here. So I learned a lot of like this kind of things from her. So getting back to the talk. So now that the ice is a little bit broken, does anybody have any thoughts on this experience, or you want to argue with me? So how do you guys identify the problems you're working on? How many of you are PhD students? Okay, so most of you. And like first year? Second? Third? So who are in the third year, how did you come up with the problem you worked on? Was it your idea, or did you just join the group and the topic was given to you?
Well, it was my problems that I identified. Basically, from reading all the researchers' work, the papers, you will specify some of the gaps that are there.
Yeah.
Then you try and work on those gaps.
Yeah. So you were given a domain, but you were given the flexibility to identify the gaps and find out. Yeah. So that's a good one. Yeah. Okay. So what I will explain you here is how we came up with the questions and the problems to work on. Of course, I'm, let's say, in the middle of my career, so I have a little bit less pressure on publishing than you guys. I have a good position, my employer is okay with the speed we are doing, and there is also a lot of real problems to solve. So I have a little bit more freedom, which is great, because I can go out a little bit of the everyday research work we do and the rhythm of 3 conferences a year, and think about the big questions and then derive the research questions from there. So it's not, I'm not, actually, you will see that we also discovered a gap, but it's a big gap. Like it's something like a topic in reinforcement learning that not a lot of people are working on, and it happened that at least what I think is that it would be very useful for the kind of systems we want to optimize. So let's start. Okay, does it work? No, it doesn't. Okay, so you all know AlphaGo and AlphaFold that just came out like a week ago. So there are these huge, visible, recent breakthroughs in reinforcement learning, although AlphaFold is not reinforcement learning. It's more generative models. But in reinforcement learning, you have these huge things, like you have Atari games, mostly DeepMind, 1,000 researchers who are there are working on this. So Atari games, Go, poker also, which is probably the last standing game where humans are better than machines. Chess, learning from nothing. So huge advances. In a certain sense, it arrived much earlier than it was predicted after chess, because Go is a much wider and deeper game. So it's great. And these are really huge advances. And the algorithms that are there are very interesting. But the question is, if you thinking about an engineering system where I'm just an engineer who's piloting a plane, it seems kind of similar to a game. Like I'm doing actions and the system responds. I have something to optimize, maybe to reach a goal or maybe to continuously optimize it. So it's from far away, it seems very much like those algorithms that were in games should be useful in every engineering system. So the question is, why aren't they there? And the answer is, it's more about partly human aspects, partly some of the things that reality presents versus games and simulators. So just so we are on the same page, what I call an engineering system in this course is like a controlled engineering system. So the best way to imagine is a pilot and the plane. The plane is the system, the pilot is the systems engineer. She observes system observables, so everything that comes through the window or comes from the system, like there are two types of observables, one that from outside and one from inside, one that she can control, some others she can't. They are all in this vector I will call O, observable. And then there are some rewards. We call reward in reinforcement learning or KPI, key performance indicator in industry. So these are indicators of that telling the engineer how well she's doing in controlling the system, like how far am I from the target, how fast I'm going, safety indicators, etc. And then what she does is she sends actions to the system, control actions. Those are the ATs. And we will discretize everything because usually it is. We have time steps, that's why it's indexed by T. And then it's a loop, right? So this is a controlled engineering system. It's a very high-level view of agents and control and reinforcement learning. Tell me anytime if I'm too fast, also if I'm too slow. I'll try to have a balance. If something is unclear, tell me. Okay, so engineer observes system states and performance indicators, O and R, tunes the parameters, A, to optimize these performance indicators, the rewards. Okay, so this is the picture. So this is the question I'm asking, why aren't AlphaGo is in these systems? Why isn't driving planes, driving data center cooling systems, or mobile towers, this is what we are working on, or cars, for that matter? Why? They are solving exactly this type of problems. Like in Go, there is a player and there's another player, so the system is the other player, and they just play this game. The question is even more interesting if you look at actually, so if I'm a startup pitching it to a VC, a venture capitalist, for money, this is my potential market. It's not necessarily the one I'm developing now, but potentially transportation, manufacturing, IT, these are all these kind of engineering systems where somebody is sitting in front of a dashboard and driving it, okay? So it's tens of trillions of dollars per year. So if you have a tiny improvement on these systems, you can have a big profit. And so this is for me, this is a very interesting question because this shows also that somehow research is not very directly driven by value in this very monetary sense. If it was, a lot of people would work on these problems. And actually there are research problems in this direction, which you will see. So just to go back a little bit to my day job, so our use cases are in telecommunications. So Huawei, we are making software, but also hardware for mobile networks. 3G, 4G, 5G, now even 6G is getting planned. But also computers and data centers, so cloud infrastructure, Wi-Fi, and so everything Huawei does is engineering systems. Even in your computer, you have fans you have to control to cool your computer, and you don't want to drain the battery, so there is something to optimize there. So we are working on data center cooling. That's Google. So DeepMind, that was one of the things DeepMind actually did really for industry, optimize the data center cooling systems of Google. So Huawei is selling data centers, and we want to sell AI with it. So the cooling consumes less energy. Wireless parameter tuning is our biggest project. So it's about wireless connections. So in every antenna, you have a software. It has about 400 parameters that an engineer tunes 4 KPIs like upload download rate, call drop rate. So when you call somebody and the line drops, it's about 0.5% of the time. This is what we want to decrease. Throughput means how much data goes through the system. So again, you want a connection when you're watching a movie that doesn't slow down the movie. So these are the KPIs that we can observe in every cell. And we have 400 parameters. The best parameters depend on, of course, the usage, the type of cell. Is it a supermarket? Is it a working area? Is it a residential area? When is the big traffic? It depends on the type of connections you have. You are watching a video or you are just browsing the internet. So there are all these things that could be in principle observed, and the cell parameters can be tuned to make some KPIs better than before. And the third one is Wi-Fi setup. So this is even something easier to imagine when you are in a conference and you have like 100 Wi-Fi antennas, and each antenna has their own parameters, and they want to make sure that everybody can connect, and usually they can't because it's tough, right? And those parameters are usually, today, they are usually fixed. So some engineer fixes them, maybe changes them once a year, depending on some parameters. It's true for Wi-Fi, mobile, and also data center cooling. So of course, there's a control system, but the hyperparameters of the control system are fixed. So our goal is to make them safer, better, more reliable, and more energy efficient. This is probably the easiest KPI to monetize, because that's one of the things I'm always saying, that the best metric for a data scientist is when the metric is measured in dollar or euro, because then I know that if I improve it by 1%, how much money I make to the company, or how much can I ask for that job. So, and energy efficiency is something that's very easy to monetize, because there is a linear connection between, well, more or less linear connection between energy and price. So this is just the tip of the iceberg, even within Huawei, let alone the full industry. So this seems to me a very important problem. So the question why reinforcement learning is not in these control systems yet, it's even more interesting. Now, of course, automation in control has a long history, right? So it's not just we are inventing this now, but most of the time, automated control is based on physics, deep understanding of physics of the system, and mathematics and equations and classical, what we call classical control. And sometimes it goes wrong. I don't know, you guys know this picture? So it's Chernobyl just before the explosion, right? So sometimes, there was a lot of automated control, and of course human control too. It's combined, and an interface between them. And so sometimes this system, but there was no machine learning, of course. Nothing was learned there. It was all based on physics. And what's happened actually, that the physics it was based on was wrong. If you know, there is the theory, and you can check it how. So sometimes this setup can go wrong, but most of the time it works. So if you see any robotic manufacturing system, to my knowledge, there is not much machine learning going on there, but the robots work because they are programmed to work, and they work very well. Okay, so let's put apart the classical control. What is AI in this context? How can we put all this, AlphaGo and or the machine learning that we developed into these systems? Well, at least one of the ways that we learn the system behavior based on historical data, also known as simulator. But most of the time when I talk about simulator, like climate simulator or even physics simulators, what you imagine is something that's based on equations and like big computers that solve the equations and then pretend to be the real system. And here what I'm talking about is how to learn that simulator based on historical data. And this is important because the systems we are working on, like data center cooling, yes, you can have some physics, like if you turn on the fan, the temperature will go down, but it's complex, it's chaotic, so a lot of times you don't have enough knowledge to build like this first principle based simulator. And wireless tower is even worse. Okay. Again, you have some physics about waves and radio, but when I turn, one of the knobs in these 400 parameters, what will happen? There is no real equations there. But we can have a lot of historical data. Somebody turned it sometimes, and we can see how the system reacts. So why not work and put AI in learning the systems? Now, the next 3 slides will be a conversation that's a little bit imagined, but not really. I abstracted it away, and it will show you the difficulties. Why AI is not in the engineering systems yet.
I have a question.
Yes.
The definition here, some may say it's more applicable to machine learning, while AI may have more general.
Yeah. I'm using them as a synonym, yeah. This slide deck is partly for selling what we do to the BUs, so I have to use AI. But yeah, I will talk about machine learning, of course. Yeah. So the conversation is between a data scientist and a BU systems engineer. A little bit simplified, but this happens like every day. So the systems engineers who is driving the data center cooling or driving the mobile tower, or actually the engineer who works on the product, comes to me, I would like you to land, and I don't know if you know this word land, this is what we use internally for things we put really in production, the AI. So I would like you to land the AI to control my engineering system, my wireless antenna, for example. Okay, so, and I'm a data scientist, a machine learning researcher, so I go there, okay, can I go and touch your system? Can I experiment with it? Can I give you an algorithm that explores? Or an algorithm that takes data with a policy which is different from your control policy? Yeah, and it will possibly break the system sometimes because we have to learn. Huh? So especially when you tell this, and the systems engineer says, oh, over my dead body, never. Okay, so, and probably this is this is the reason why AlphaGo is not in mobile antennas, because AlphaGo didn't care about losing zillions of games before learning how to play Go. It didn't hurt anybody by losing in the simulations. Whereas if I turn off all the fans, the electricity consumption of the cooling system is 0, but it's probably going to, boil everything or melt the data center. And the systems engineer's only responsibility is to make sure it does not happen, or Chernobyl does not blow up. Okay, so there are these technical and human things in the system which make it very hard to apply those beautiful algorithms. Okay, so next question. Okay, I can't touch your system, but do you have a simulator at least? How do you train a pilot if you don't have a plane simulator? Because this problem comes the same way when you train a systems engineer. Like, you cannot put somebody on a data center cooling and play with all the knobs, like it's not a video game. So usually people have some simulators. For example, airplane simulators are pretty good, but data center simulators are not. So sometimes we have experimental data centers, or sometimes we have the red button. I will have a picture on that. The red button is like the instructor can press it to bring the system back to a safe state when something goes wrong. But most of the time, these simulators are not good enough to be trusted, especially if you want to optimize some algorithms on it. Machine learning is really good to go to the bugs into your simulator. It will learn the bugs. If it can exploit the bugs to improve the metrics in the simulator, it will. So anything you have on the simulator that's not like reality and that makes the simulated world really looking nice, machine learning will go there, and this happens a lot. So actually we are very good at optimization, and sometimes it hurts when we go from simulator to reality. And so the last one is where we ended up. It's like a niche. I'm not completely sure yet whether it will work, but it's a niche. So, okay, I can touch your system. You don't have a good simulator, but at least you can log your data. What the control policy you have today. I can get access to the data, and I can learn something on it. And I learn it. I design a simulator, I give you back the simulator so you can check it whether it behaves like the real system. And I will modify your control algorithm a little bit, and then you put it back on the system. Of course, you will have full control. So if the control algorithm I give you suggests you an action, you can override it, because it's your responsibility. But maybe we can get into a loop like this. And this is where we get what I call iterated batch reinforcement learning. I will explain why the terminology. So just, you know, if you have to do this, if after your PhD you go to an industrial research, a lot of times what I feel is that the problem is like it's cultural, and the way we did R&D like 30 years ago, and we do R&D on AI today. So at least in our company, my feeling is that what the systems engineers think is that they have a problem, a complex problem, so they give it to the research department. Every big company has a research department. Here is my problem, do the math, solve it, and give me back the solution. And this worked for certain types of problems, but not in AI, where in AI it's a collaboration between the user. The user is the data provider, and the user is also the provider of the problem. We have to figure out what the matrix is with him. So, okay, you have a vague description of a problem. We describe what we need: data, access to the system, metrics, maybe an experimental setup. And then we design the tools to provide the data, maybe annotate the data. We have to label them if it's supervised learning. And also the interfaces of the AI algorithm, because at the end of the day, there are very few companies like Criteo. So Criteo automated the full pipeline from the user arriving on a web page to the monetization of the thing. And in the middle, there is an AI algorithm that predicts the click-through. So it's embedded into an automated loop. But most of the time, the AI block is sitting here, and there's a human here, there's a human there. So somebody is looking at the output of the AI algorithm. So we need these interfaces between the human engineer, like dashboards, and the AI algorithm. And that should be designed with the systems engineer in mind. And that's product management, that's UX. It's nothing to do with AI almost. And then we iterate. And our goal is to design the algorithms, but the algorithm is a tiny part of this. Okay, so I'm just putting this. It's a broader subject. I have a lot of thoughts on this. It's just, you know, the thing I'm talking about is one example of this. So let's back to the picture, and let's state the three things that we observed. First is that when we want to learn the system, it's not going to be an online thing. It will be offline or batch. Those two terms are usually used as synonym. So what it means is that we get system traces: time, stamp, observables, actions, and rewards, and then a CSV file typically. It's small. We don't have the zillion examples that you can do, because it's not a question of computational power. These are physical systems. They have clocks. They will not give you, you cannot accelerate them and have more and more system at a request. So they are small, typically maybe 10,000 steps if you're lucky, or 100, but sometimes it's just 1,000 or 2,000 time steps. And the last one is safety. So we cannot lose while we're learning. Okay, so these are the three things why AlphaGo is not in airplanes. So one of the papers I put on the syllabus is this, because it's very instructive and it's easy to read. So engineering systems per se are not in reinforcement learning literature. I don't really find so very applied ones, but not in the mainstream. Robotics is, and robotics and these engineering systems are not very far from each other. So this paper is about robotics. I will have another slide where I explain you the, or maybe here. Yeah, it's here. So what's the difference between robotics and engineering systems? So in an industrial setup, it's pretty much the same thing, like robots are the automated engineering systems. But when you go to reinforcement learning research, most of the people are shooting for, I think, AGI or, you know, trying to mimic humans in a deep sense. So the type of problems typical robotics labs solve is that my reward is very far. It's like a go. Am I doing a good move here will be only verified at the end of the game. So I tell to the robot some task that's very far in the future, like grab that glass and put it there. And the robot is here. So it has to learn to move, has to understand the scene, has to do everything, like, of course, like humans. But in industry, this is not like that. It's usually what we have is a continuous reward. Like we controlling something, you know, we can measure the reward in the wireless tower. Every 5 minutes you have a measurement, or maybe even faster, and that tells you how good you are doing. So this problem of having like a delayed reward, which is very tough, and because it's tough, it's in research. This is not really an important problem in the engineering systems we are working with. Which also means that the algorithms that solve that particular problem are not that useful. They are solving the problems we don't have. The other thing people do in robotics, and that's also very interesting, is robots have a lot of sensors, and you can put a lot of sensors on them, like low-level sensors, like what are my angles, what the world is. And engineering systems are designed that way because the engineer who has to control the plane has to have a very concise number of measurements on the system. The dashboard of a plane cannot be infinite. And you have the image of the scene outside, but most of the things you do based on those measurements, right? Whereas what people like to do in research is vision. Vision is big, you have deep learning, convolution nets, etc. So it's a rich set of problems where you can play with. And if you go into robotics, a lot of people are putting vision in the robots. Why? Because we have vision, right? And the problems when you have a camera on the robot and the camera is looking at the cup is very different from the problem when, you know, the cup is already described by 3 features and I have a CSV file with these 3 features. It's a representational problem. It's a computer vision problem, and they couple it with robots, which is good. I mean, it's a very interesting subject, and it's probably something we have to solve if you want to have AI. But again, this is not necessarily a problem we have in a wireless antenna, where we have maybe 50 variables we're looking at, and those variables are designed such that the systems engineer can control the system based on them. Okay, so so this paper is still very good because the algorithms that they are using in robotics, there are some commonalities. One is that they are physical, so they don't get faster with computers, like computers, and so we will not have infinite data. So this thing of microdata, it's common. So on some research, the dimensionality of the space where you're not doing this vision thing, it's also small. So that's another commonality between the engineering systems and us and robots. Yes? You mean add?
Because you talk about microdata.
Ah,
So I guess there's also ways to augment your data and like kind of tackle this problem.
well, augmenting would mean a simulator. And actually, that's a very good point, and this is where we are going. So you will see that the idea of iterated batch reinforcement learning is that you gradually learn a simulator of the system, and then you learn your controller on the small data set you have from the system and on as much data you want from the simulator. So you can play that game also if you have a real simulator. By real, I mean physical, based on physics. The issue is always the difference between the simulator and reality, and that's again something that we don't really tackle in machine learning textbooks, is that the oracle that gives you the data is not the same as the real data, right? So you have like this systematic difference between the two systems, and there is no real theory about how to deal with that. But the point is very good, and this is actually the direction we are going in. So this ends the first part, the why. And what I would suggest then, because it's hard, I know it's hard to ask questions, I've been in your shoes. So let's do the same thing as in the beginning. So you turn into pairs, and then you tell to each other what you expect from this course, what you learned here, if you have any ideas about what I just talked about, and maybe then you can ask me questions. So let's have like 3 minutes for just discussion between you guys, okay? Yeah. Turn me on. Okay, thank you. Okay, thank you everyone. So now tell me what you got to and ask me the questions or challenge me. Who wants to start? So everything is clear and you all agree. Anybody? Yes? No? Okay. Okay, in that case, we'll start the second part, which is the what. I already got into a little bit into the what, but now we will formalize it. So this is iterated batch RL. And why are these adjectives on RL? Because RL has different flavors, different types. One is online. When the algorithm is sitting on the system and at every action it can do something to change its internal workings. It has only one shot, so it's like an infinite system or maybe episodic, but you do learn online and you do learn constantly, and then you got to somewhere where, let's say, you trained and then you're fixed. And then there is batch RL. So batch RL is closer to supervised learning in this paradigmical sense. Like I give you a data set of that type. So the data set here will be at like a time-stamped time series of actions, observables, and rewards. This is what you control. This is a system and external variables, and this is what you want to optimize. I give you a single data set. I hope that the actions were, covering the space of the possible actions, which is usually not the case, but let's say they are. In benchmark research data sets is the case. And then I give you this data set and you give me an algorithm, a trained algorithm. So it's like a one-shot training of a control algorithm. What does the control algorithm do? The control algorithm takes, and sorry for that, the discrepancy between S and O. S is state, O is observable, and there is a slight difference because it might not be the same thing. But in this course, O will be the same as S. So my state, based on which I'm taking the action decision, is just the current time step. Okay, so everything I observe, those 50 variables I observe in my wireless antenna, I do an action. Okay, so the control algorithm is a function that maps the observables at time t to the action at time t. Let's say like it's a single action variable that you turn a knob or you press a button. It can be discrete or continuous. Okay, so the controller is either a function, so it can be a fixed, deterministic function. So for the same observables, you always do the same action. Or it can be probabilistic, so that's pi, which is a probability distribution on A given the observables. And then again, you can use the most probable action or you can sample from it. So those are other questions you have to decide in the controller. But in any case, this is what the controller will do. And so in batch reinforcement learning, I just give you a single data set and you give me an algorithm and you're gone. And that algorithm is then maybe tested on a simulator, on a real system, and you show plots. Okay, but there is no going back to learning. Okay, so that's pure batch or offline RL. And what we have here is a mixture of the two. We are not online, we are not sitting on the system, we cannot learn after every action, and we sometimes don't even control those actions, but it's not a single shot. I can design a project with the wireless BU where every month we do what we call a live test. So we start by getting a data set from the policy, the control policy they are using right now. I do something. I give the algorithm back to the engineer, and the engineer tests it. Okay, so I'm the data scientist. I design the control policy. It goes back to system engineer, and the system engineer tests it and logs it again. Logs the output of my algorithm so I can check how well it worked. and then we iterate. It's not a rapid iteration, so it's not in the computer, it's in reality. So maybe we can get like 10 iterations a year if we are lucky, but it is an iteration. And so there is a big difference between a single shot and the iteration is what we call exploration. So when I have a single shot, my only goal is to optimize the reward after that single shot. But when I know I can go back, I also want to design algorithms to collect the data for the next iteration. And especially in the beginning, because what happens with real control policies is that they are what we call very narrow. So they use a very small number of actions because they want to be safe, they want to understand what happens. And so they don't want to like randomize actions, they don't want to play with a very broad set of actions because they are afraid of breaking the system. So the first data set we get is usually very narrow, which means it's really hard to offline optimize it because for the same state you always try the same action. You don't know how other actions will do. And this is essentially what we have to figure out if you want to train an algorithm. You have to see which is the best action in a given state. And if in every state there's only a few number of actions that were tried, it's hard to learn. So the first thing we have to do is exploration, really. So we give them, let's say, okay, randomize your policy, or you do random actions, and sometimes it works, sometimes they say no because we're afraid. But in any case, like conceptually, technically, it's a very different problem from the single shot offline. So this is why we are in this domain of iterated batch or iterated offline reinforcement learning. Okay, so we like it because it fits the organizational scenario I just described. So this can really happen that we have these data-taking campaigns. And it's actually very similar to the supervised learning loop that I explained in the beginning, that you have these campaigns of data taking, retraining, retuning, and putting it back to production. It's also technically doable. It's not like something, it's not a dream, it's not AGI. And interestingly, it's not that well studied. So you have offline RL, a lot of things on offline RL and concepts and algorithms. You have online RL like AlphaGo, but this thing is not really on the map. It exists, but not very well studied. So we sort of have to create the domain, and you will see that one of the things on the how part, like how we do it, we have to design the domain, including the metrics, the experimental setup, etc. And so this is at the same time exciting because it's like a new territory, but also tough because when you want to publish, it's not only the solution. I mean, if you improve the score on Cypher or ImageNet, that's a slam dunk. It's easy to publish. But if you say, I have a new problem to solve, and here's the problem, and I have to argue why it's an important problem, and here is, by the way, the baseline algorithm that we designed, that's a much tougher sell, especially today where reviewers are all over the place and not necessarily understand this paradigm. Okay, so the next picture, and this is the most complicated I will show, is the model-based. So you can do iterated batch offline RL from going the data to the control algorithm. There are algorithms that do this. But we prefer going through a system model. So we do, the controller will be there at the end, but the first thing we do with the data set is that. It's a little bit more complicated than the formulas there that I will do. But basically so the first line is this connection between states and observables. Sometimes the system is non-Markovian in the sense that the current observables don't give you the full picture. You have to go back in history. Okay, and in this case, your state might be a function of all the history. So this is the first line there, but I will not use this. This will be not an issue here. You can just say ST is equals to OT-AT. So the pair of, actually OT, because AT depends on OT, but it can be the action just before. Yeah. Yeah, no, it's OT-80, sorry, because what the system model will tell you is what is the next observable given the current state and the action. how will the system evolve if I do this? It's a simulator, right? It's the same thing. And the two lines are there because sometimes you are modeling the observables and the rewards separately, but in our case, the rewards are a function of the observables. So it's enough if we model the observables. So basically, we do this stochastic simulator. Why stochastic? I will explain you what the rationale is to be probabilistic, not deterministic, and whether it's necessary or not. That's one of the scientific questions we have. But in the most general case, it's a stochastic simulator, which means it's not telling what the next state will be. It tells this, the probability distribution over the state space or the observable space, given the last observable and the action. Okay? And then once we have the simulator, the nice thing is that we can do two things. We can just give the simulator to the engineer, and humanly, it's a very good move. It's like, imagine a pilot who has to trust a simulator to train another pilot, like he's the teacher. So he would like to check out the simulator, whether the simulator is good, right? So he sit there and drive the simulator, and if the simulated airplane reacts the same way as his experience tells him, he'll be okay with it, to give it to a student. So we have a sort of similar dynamics here. So if we give a simulator to the mobile engineer, and he tries to control those actions, and it behaves the same way as the real system, he will trust it that based on the simulator, we can learn a good control policy. So that's the last point here. Why as model-based offline RL? So model-based RL in general, that's one of the orthogonal directions, model-based or model-free RL, is considered the best approach where you don't have a lot of data. So actually, and this is the last point, is that, look, we have this data set. One thing we can do is just to learn the simulator, right? And if it has any more information, any usage, then it's a good thing to do. We have a lot of time between these two live tests. We have this data set which is not very big, so let's just learn the simulator. So it's sort of like the same idea as what Jan LeCun called self-supervised reinforcement, self-supervised machine learning. Like we have this lot of pixels in a picture. Let's just try to, for example, learn cover a patch in the picture, and let's try to learn what's there. So things that for which we don't need labels, like human labels especially. This is all self-supervised. So high dimensional data. Let's start to learn these dimensions from other dimensions. So this is sort of like the same idea here. Like we have this data set. The simulator seems to be a reasonable object to have, and we have the data set, we can learn it. It's a supervised learning task with non-iid data, but it's still supervised learning, you will see. So it's a relatively well-studied and easy task, and we think that it's also useful for learning the control policy, and you will see it is. And one counter-argument for model-based RL, there is one, which is that here I'm learning the full system, all the observables. I have a function that outputs all the observables at next iteration. Whereas people who think about vision plus RL, so images, cup, grab the cup, bring it there, drink, it's true that it's probably not really meaningful to learn a model for every pixel of your vision, right? Because a cup is there, you just want to learn the really important features and maybe a model for those features. So you have this, again, this representational step where you have to take a huge dimensional object, the image, and extract the important information from it. If you think about the control task, to control the cup, I don't need to predict what's going to happen in that pixel, right? So what people say about model-based reinforcement learning is that it wastes a lot of power for predicting things that we will not need at the end for the optimization. Okay, and this is a valid argument if you are in that situation, like you're controlling Atari games. You probably not need to. You don't need to predict every pixel. Go, it's a little bit less clear. Yes.
The one remaining question is, how do we know that that pixel is not necessary?
Yeah. Of course. So this is just an intuition, and that, of course, technically that's the big question. Like, how do we know which is the observable we want to model? But those algorithms try to figure that out, solve that problem, and maybe not even go through a model. Have like a latent representation and learn the controller directly from there. And dual, of course, it's mostly online RL, model-free and online. So model-based, model-free offline, that exists too. Like I give you a data set and you don't go through the modeling part, you just give me the controller directly. There are some algorithms there too, in that space. Yes? How?
How is the distribution model, so you said, well,
Yeah.
that's an example. What is the distribution model? How is it set? Do we have knowledge of it?
Yes, so the question is how do we design that probability distribution? But that's going to be the second half of the course after the what, the how part. Yeah, that's mostly what I will talk about technically. Yeah.
I was wondering whether if you have a system from which you cannot collect data, is it possible to validate the simulator in some other way? Because sometimes the real system is not accessible.
Well, either you have data and you do this, like learn, or you don't have data but you know the physics of the system and you design, differential equations and like a climate simulator. And then you can do hybrid. And a lot of things I will talk about is this, what is the smart way to do this hybrid? The big question is always that the simulator is not reality. So you have a transfer problem which doesn't exist really in supervised learning. We are getting there, so out of distribution and distribution shift and transfer learning, these are big topics that are actually coming up a lot, like this year. So we also have a transfer learning branch in the team, and it's exploding because this is a real problem. So the things are not IID and not identical and not independent. Here we just lose independence with the time series, but it's also not identical. So how to do this? Yeah, these are the big questions. How do we do this? Because these are like systematic errors, not statistical. Okay, so this is the counter-argument for model-based RL. But my counter-argument to that counter-argument is that in the type of systems that we are working on, we don't have this because we are not working with images. We are working a relatively small set of system observables that were designed by engineers, like the pilot, like the airplane dashboard, so that the control engineer can control, the systems engineer can control the system. So we probably don't waste that much power predicting all of them, right? So these are the arguments for model-based RL. We also do model-free RL in the team, partly because some people in the team like it and they want to go in that direction. So it's always a balance between my vision and what people come from and what they want to do. But we put together you will see a nice research plan where actually model-free RL has a role in this loop. First of all, there are some model-free controllers, especially in the single-step offline reinforcement learning. So when I give you the data set, you give me the controller, there are some algorithms that are interesting for us to see because we are sometimes in that situation. But the most important point here is that, okay, let's say now I have a simulator. The simulator is like the AlphaGo. It's like it's in the computer. So now on that simulator, I can use model-free or online RL, model-free and online RL, to learn an agent. So I can have my agent who controls the simulator very well. Whether it transports to reality, that's a big question. But still, the agent that we learn on the simulator is something we want to do. So, and there, model-free, offline, and even online RL are interesting. So these kind of model-based reinforcement learning planners, so I will explain all those words later, this is called Dino style. So we learn a simulator, on the simulator we do whatever we want, we learn an agent, and then we do a modified version of the agent, we put it back on the real system. And the third direction we have in the team is we call it contextual bandits, but it also goes under the name of like Bayesian or zero-order optimization, where the difference is that in reinforcement learning you usually have either a very late reward, like a sparse late reward that you have to sort of backpropagate through time, or you have a delayed effect. So you don't see the effect of your action right away after you do the action. But a lot of times in these systems, the effect is very short term. So you turn a knob and you see right away the effect. And in this sense, that's not reinforcement learning. That's something which is simpler. It's called bandits if you have a single system. But here it's so-called contextual bandits because you have a state. You still have a state that describes. So the best action can depend on that state, but the reward will be immediate. That's contextual bandits. And it's also like zero-order optimization, like you have a space of states and actions. You control the actions, and you want to find the best action in that state. Okay? So that's an optimization problem where there is no question of longer-term optimization. So based on this, we came up with this 3-4 year research plan, and this was very interesting to this process of coming up with this. So I have 6 permanent researchers and about the same number of research engineers and PhD students, and we sat down who wants to do what, who likes this, who wants to work on what. A lot of things were already in place when I arrived, and we came up with this with the different subgroups where we do all of this slowly but surely. And that actually was really nice because most of the times, you know, before in academia, we didn't really have like a long-term research plan. It was mostly ad hoc, maybe 1 year, maybe next conference, right? What do we do for NIPS or new RIPS? And this, for the team, it's really nice to have something like this where everybody has their place and we see where we are going in 3-4 years. And it's also good to project it towards the BU so they know what we are going to do. Now, of course, in this course, I will not talk about all this. So I just highlight here what we will talk about. And it's mainly the first point. We'll see if we can get there. It's not there in the slides yet, so we see also how the time will go. But the first, so it's exactly the question you asked there, like how to choose the models, this probabilistic or deterministic models. That's one of the questions we have, whether it's deterministic or probabilistic. What would be the criteria? Because if you have to run through the machinery of reinforcement learning every time you change the hyperparameter, that's going to be a long experimentation. So we want something where the system models can be tuned without going into the dynamic system. On what system we will do this, because we cannot touch the real system, so we have to come up with some kind of toy or benchmark, or have to look in the literature. We also want to publish, so it's hard to publish if you come up with a system that's not available. What are the metrics? So how do we measure success? How do we measure whether like this model is good for reinforcement learning without actually going through the loop? What would be the methodology to figure out how those metrics interact between the model and the dynamic system? And then the algorithmic development. So what models? If you go to generative models, you have GANs, VA, flow, autoregressive models, you know, mixture density, a lot of things that you can try. So what are the requirements for the models, and how do we choose out of this and then implement them and test them with the metrics we came up with. Okay, so this is the same, because I was thinking about so what I wanted to talk about here again, that it's the two paradigms, the scientific and the engineering. So the engineering would be design a simulator, design a controller that works best for this problem. Okay, and iterate. Have ideas, iterate, improve, iterate again, improve, and then have a solution for the BU as fast as possible. So that's like an engineering paradigm. But we also want to publish, and we also want to know. I'm very curious about that question, like how to choose the models and what are the properties of the models that are important in general. So it could be wider than just this particular application, right? So we will do this hybrid. So I will show you how we went ahead to solve the problem and what are the scientific questions we asked, what were the experiments we designed to make sure that we are getting to the target, so that's also experimental, but also to answer some of the questions, like do we need, like just give you an example, I will have a list, but do we need here generative models or deterministic models? And that depends on how they are used, you know, and a lot of things. So it's a very high-level question, which is hard to answer because maybe a deterministic model with this controller works well, and this probabilistic with that controller works well. How can you answer that particular single question without going on into all the engineering details? Okay, so this is tough. But I'm still interested in and want to know, like, on certain kind of systems we need probabilistic models, certain kind of we don't. Why? What makes that system needing probabilistic models or deterministic models? And that's only one question. I will have like 3 or 4 of those type of questions. And I think it's time. So that was the first third of this course, and now I feel that we have enough material for 4.5 hours. And so please, you know, discuss it during the break and come back with questions. I really want, you know, to hear your opinion, and if anything is unclear, ask me, okay? So see you in the afternoon.